Let me start with a simple idea. Imagine you have extra electricity, and instead of wasting it, you use it to lift something heavy, like a giant concrete block. That might sound too simple to be true, but that is actually one of the oldest and most reliable ways to store energy. You store it as height. When you lift a heavy object, you're not destroying energy, you're saving it. You're storing it as what we call potential energy, meaning energy that's waiting to be used later. Then, when you need electricity again, like at night when the sun isn't shining, you lower the block down in a controlled way, and that movement turns machinery that produces electricity again. So this whole system works like a battery, but instead of chemicals, it uses gravity. Most of us think of batteries as chemical devices, like the battery inside your phone or laptop. But this is different. A gravity storage system is a mechanical battery. Here's the simple comparison. A chemical battery stores energy inside chemical reactions. A gravity battery stores energy by physically lifting a heavy weight. So when electricity is cheap or abundant, maybe because wind turbines are spinning hard or solar panels are producing a lot, we use that electricity to lift heavy blocks. Later, when the grid needs power, those blocks are lowered slowly and safely, and that motion is turned back into electricity. Think of it like winding up a toy car. You store energy when you wind it, and you release that energy when you let it go. This slide shows the full cycle in two simple steps: charge and discharge. Charging is when we store energy. We take extra electricity, often from solar or wind, and we use motors to lift heavy blocks upward. The higher the blocks go, the more energy we store. Discharging is when we release energy. When electricity demand rises, like in the evening, we lower those blocks back down. As they descend, they turn generators and produce electricity. So the system is basically doing one thing. It converts electricity into height, and then converts height back into electricity. And the best part is, gravity never takes a day off. It's always available. This idea may sound new, but it's actually very familiar. It's similar to how hydropower dams store energy. In pumped hydro, we use extra electricity to pump water uphill into a reservoir. Later, we release the water downhill and generate electricity. This gravity system works on the same principle, but instead of water, it uses solid blocks. And instead of a mountain and reservoir, it uses a tower and cranes. So if you already understand water stored uphill, then you already understand gravity storage. It's simply heavy mass stored up high. Now, let's talk about why people are excited about this. First, it helps renewable energy. Solar and wind are great, but they are not constant. The sun sets, the wind slows down. This system helps smooth out those ups and downs, so electricity becomes more reliable. Second, it uses simple physics. There's no mystery, no complicated chemistry, just steel structures, motors, cables, pulleys, and concrete blocks, things engineers understand very well. Third, it can last a long time. Chemical batteries wear out over time, but a mechanical system, if maintained properly, can run for decades. And fourth, it can be more environmentally straightforward. It avoids depending heavily on rare metals like lithium, cobalt, or nickel. Instead, it relies on materials we already know how to manufacture and recycle. At this point, you might be thinking, okay, this sounds interesting, but is it real? And this slide answers that clearly. Yes, it has been built. Not just in a lab, not just as a computer model. It is a real system that has been connected to the electrical grid. That's a big milestone, because grid connection means the system is working in the real world, under real demand, real weather, and real operating conditions. So gravity storage is no longer just a theory. It's a functioning technology. This slide gives the project details of a real facility. It shows capacity, 25 megawatts, or 100 megawatt hours. That means it can deliver 25 megawatts of power, and it can keep doing that for several hours, depending on how it's operated. It also shows the developer, Energy Vault, the location, Rudong, Jiangsu Province, China, near Shanghai, and the status, construction completed and grid connected in December 2023. The key message here is simple. This is proof that gravity-based storage can operate at utility scale, meaning it can support real power systems, not just small devices. Now we move from the idea into the real engineering challenges. Here's the problem. This system is heavy, very heavy. And it's not just heavy once. It's heavy in a way that changes all day long. The slide explains that this site is on coastal ground with soft soils like soft marine clays, silts, and alluvial deposits. These soils can be weak and compressible, meaning they can squeeze and deform under heavy loads. So the big engineering challenge becomes, how do you build a tall structure that repeatedly lifts and lowers massive weights without the ground slowly settling, shifting, or becoming unstable? This is where geotechnical engineering becomes the foundation, literally, for the entire system. This slide focuses on a very practical risk. If the ground is soft, heavy loads can cause settlement. Now, settlement means the foundation sinks down slightly over time. And the worst kind is differential settlement, where one part sinks more than another. Why does that matter here? Because this is a precision system. If the tower tilts or the rails misalign even slightly, it can increase wear, create safety risks, and reduce performance. So what's the solution? The slide highlights 3 strategies. Deep foundations like piles. These transfer the load deeper into stronger soil layers. Ground improvement. This strengthens the soil below the tower and crane pads. Monitoring. Engineers watch the settlement in real time during and after construction, so they can detect movement early. In short, if the soil is weak, you don't hope it works. You engineer it to work. This slide introduces a very important concept: repeated loading. A normal building is heavy, but its weight is mostly constant. This system is different. It lifts and lowers blocks again and again, thousands of times per year. That repeated loading can slowly change the soil behavior. The soil may lose stiffness over time, meaning it becomes slightly softer and more prone to settlement. This is like bending a paperclip back and forth. The first bend is fine, but repeated bending weakens it. So engineers address this by doing advanced modeling to predict long-term effects, using conservative design limits, and building tolerances into the structure so small movements don't cause failure. This is not only about strength, it's about durability over years of operation. This slide covers 2 more real-world problems: water and sideways forces. Problem A: high groundwater. Coastal areas often have shallow groundwater. That creates challenges during excavation and foundation construction. Water can flow into excavations, soil can become unstable, and upward water pressure can push against the structure. The mitigation includes temporary dewatering during construction and long-term drainage and waterproofing. Problem B: wind and seismic forces. This tower is tall and slender, and it carries heavy moving loads. That means it must resist sideways forces like wind and potentially earthquakes. The solution is deep pile groups designed for both vertical and lateral forces, and soil structure interaction modeling, meaning engineers study how the structure and ground behave together. So the message here is, it's not enough for the tower to stand up. It must remain stable in wind, water, and long-term operation. This slide summarizes the whole engineering story. It lists the main issues and how they were managed. Soft marine clays can cause settlement. Use deep piles and soil improvement. Cyclic loading can cause long-term fatigue. Use cyclic soil analysis and conservative design. High groundwater can cause instability and uplift. Use dewatering, drainage, waterproofing. Seismic and wind loads can affect lateral stability. Use pile groups and soil structure interaction modeling. Heavy construction loads create risk during building. Use temporary platforms and monitoring. So what we're really seeing is this. Gravity storage is simple in concept, but serious in execution. It requires careful foundation engineering because the ground is part of the machine. This final slide brings everything together. The message is, this project wasn't about inventing new physics. It was about taking proven engineering methods like deep foundations and soil improvement and applying them to a new type of energy storage system. And that's important because it shows gravity storage is not just a clever idea. It's something that can be built, operated, and scaled. In a world that needs clean energy and reliable power, gravity energy storage offers a practical solution. Store renewable energy when it's available, and release it when people need it most. In simple terms, we're turning heavy blocks and gravity into a grid-scale battery.